Okay, so the lab that we're working on today is experiment 11, known as moles and chemical formulas. So in this lab, we're going to determine the simplest formula of a compound, known as the empirical formula, calculate the amount of water in a hydrate, and determine the formula of a hydrate. So the recommended reading is experiment 11, moles and chemical formulas, and you'll also see some content in the chapter 4 notes that'll be posted next week that will help you with this lab. I summarized the chapter 4 notes and put that content in the introduction section, and we'll be going through this content in our pre-lab lecture. For now, I'm just showing you where everything is, and we'll talk through and explain how this lab functions. Okay, so the theory behind this lab is written in the introduction section. In terms of what we are actually doing, in today's laboratory, the first part, which is part A of our lab, which is experiment 11, just to show you what this would look like in your lab manual. If you open up your lab manual and go to the page title and go to the section titled Experiment 11, Moles and Chemical Formulas, I have found videos that exactly match the procedure for experiment 11. Is everyone able to find experiment 11 in their lab manual? Is everyone able to find experiment 11 in their lab manual? So, for part A, finding the simplest formulas, for this procedure, we're going to be looking at the reaction of magnesium and oxygen in a crucible. What I have done is I have found a video where it shows the complete procedure for the reaction of magnesium and oxygen to generate magnesium oxide. Now, throughout the video, there are pauses where they show the raw data collected. Does everyone see how we have a balance and we're taking a mass reading from the balance? You're going to take that data for each step, and you're going to fill in the given spots in the data table. Okay? So like in this case, initially they're measuring a crucible. So you're going to record the mass of the crucible in this section. Likewise, when they add the magnesium, you're going to then record the appearance and mass of the crucible and the magnesium. Does that make sense to everyone? Does everyone see how the video matches what data you're collecting? Any questions on that so far? So that's part A. So what they're going to do is they're going to react the magnesium with oxygen in a crucible. It will begin to glow as it reacts with oxygen, and at the end will generate magnesium oxide, which, as you notice, has a substantially different appearance and it has a different mass. Once they finish the heating process, they then weigh their final product, and this final product is what you'll use for the oxide product mass. Now, from just these 4 pieces of raw data, you'd be able to calculate the empirical formula, and I will show you how to do that in today's lab lecture. Okay? Now, that's part A. Does part A make sense to everyone in terms of where you're collecting the data and how you're collecting the data? So you're going to watch the video and collect the data at key points. For part B, as an overview for part B, we're looking at the formula of a hydrate. And just like before, they're taking their measurements using a crucible and a balance. Allow it one moment while the video loads. So you're going to watch the video for the magnesium sulfate hydrate lab. So each time they pause the video to take a measurement, that's where you're collecting your data. So like this number is what you'd use for your empty crucible. That's why the video pauses. Then they add the salt, which is your magnesium sulfate hydrate. This is your hydrate. And after they finish adding their salt, takes them a little bit, then they pan to the balance once again, and you'd use this for the mass of your crucible and hydrate. They then heat the sample to drive off the water, and they weigh it multiple times after each heating. Once they've finished the heating process, then you'd record the final mass in your data table. And from these 4 pieces of data, you can in turn calculate the amount of water present in your hydrate. Does everyone understand how part B is going to work in today's lab? Does everyone understand where to collect the data in part B? Okay, now what we're going to do is I'm going to give a lecture and overview of the calculations and theory behind today's lab. So I'd encourage you to take notes during this time. And this is content that we'll cover again in chapter 4, but I want to make sure that we have enough of a background from this pre-lab lecture that we can start today's lab. Okay, so let's go over some basic terminology. This lab focuses on what's known as the empirical formula. The empirical formula is the simplest ratio of atoms in a chemical formula. So the empirical formula is different from the molecular formula, where the molecular formula indicates the number of atoms of each element in a molecule. So for example, if our molecular formula was N2O4, our empirical formula, which is the simplest ratio of atoms, what would the empirical formula be in this case? Is there a simpler ratio of atoms?
NaO2.
Yep. So we get NO2 as our empirical formula. Exactly right. So the empirical formula is the simplest ratio of atoms in a chemical formula. In other words, in this case, if our molecular formula, we have 2 atoms of oxygen per 2 atoms of nitrogen, we can simplify it to 2 atoms of oxygen per 1 atom of nitrogen. Now, what's really interesting is that 2 different compounds can have the same empirical formula. So for example, N2O4 and NO2 have the same empirical formula. Does that make sense to everyone? Now, how do we determine the empirical formula? Now, to do that, we're going to need to first talk about the idea of mass-mole conversions. So mass-mole conversions, how do they work? Well, we know that the atomic mass, so for example, the atomic mass in the periodic table for oxygen, so this atomic mass indicates the mass of a single atom. So for example, this mass is 16.00 AMU per atom, where 1 AMU is about 1.67 times 10 to the negative 24th grams. The atom has a very, 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 very small mass. Now, obviously, our balances weigh masses in grams. So even the smallest mass that we can measure on our balances contains a very large number of atoms. So rather than looking at a single atom, what we're going to do is we are going to count a large group of atoms. And the method of counting that we use, so rather than a dozen, so we know like a dozen of something, so like a dozen eggs, for example, would be equal to 12 eggs. So we count a dozen, that corresponds to 12 eggs, right? If I said I have a dozen atoms, how many atoms would I have? How many is in a dozen?
12.
12. So we'd have 12 atoms. Okay, so rather than a dozen, what we're going to do is we're going to count a mole of atoms. So 1 mole of something is 6.02 times 10 to the 23rd. So for example, a mole of atoms would be 6.02 times 10 to the 23rd atoms. Just like a mole of eggs would be 6.02 times 10 to the 23rd eggs. It's just another method of counting. It's just used to count really large amounts because atoms are so small. Does that make sense to everyone? This idea of a mole, it's just a really large number of something. And we use a mole to count atoms and molecules and count groups of atoms and molecules. Does that make sense to everyone? Is everyone comfortable with that idea?
Yes.
Okay. So in 1 mole, so let's pretend we're looking at oxygen now, oxygen atoms. 1 mole of oxygen atoms. So we have 6.02 times 10 to the 23rd oxygen atoms. If we put that on a scale, the atomic mass is equal to the mass of 1 mole of atoms of that element. So if we put a mole of oxygen atoms on a scale, we'd see a mass of 16.00 grams. So oxygen has a mass of 16.00 grams per every 1 mole of oxygen atoms. So this form of the atomic mass, known as the molar atomic mass, is the most common way that we use the atomic masses in the periodic table, because we can physically weigh out 16 grams. We can handle masses on the scale of grams easily. So when we think about samples of an element or a molecule, we like to handle things, and we like to handle our chemical species in the scale of moles rather than on the scale of atoms. So if we look at large groups of atoms, we can actually observe and weigh these large groups of atoms, and we can record the mass of this group of atoms, this mass of our sample, more easily. Does that make sense to everyone? Does everyone understand how the atomic mass is related to the moles of atoms? Does this idea make sense to everyone?
Yes.
Perfect. So, why is this important? Well, just like we can use and calculate a molar atomic mass, we can also calculate what is known as a molecular mass. And the molecular mass is the total mass of all atoms in a molecule. So let's do a relevant example. Let's do a relevant example here. Let's look at the molar mass of magnesium oxide. So simply all we have to do is take the mass of magnesium times the number of magnesium atoms plus the mass of oxygen times the number of oxygen atoms. So I'm going to need everyone to help me out with this. What is the mass of magnesium in the periodic table? And let's use the mass in terms of gram per mole. What's the mass of magnesium? 24.31. Okay, so we have 24.31 gram per mole. From our formula, how many magnesium atoms do we have? 1. Okay, for oxygen, we already established it has a mass of 16 gram per mole. And how many oxygen atoms do we have? In our formula, right? 1, just 1. So focus on the number of atoms in your exact formula. So if we add our masses together, we get 40.31 grams, and this time it's per mole of magnesium oxide. So what this is telling us is if we get 6.02 times 10 to the 23rd molecules of magnesium oxide. This time we're looking at molecules, and if we put it on a scale, we'd see a mass of 40.31 grams. So rather than looking at the mass of a single atom, we're looking at the mass of a set of we're looking at the mass of a molecule and the mass of a mole of molecules. Does this example make sense to everyone? Does everyone understand how we're calculating molecular mass? Any questions on this idea? We just add up the mass of each of our atoms. Does that make sense? Any questions? Yes. So let's do another example. And let's look at the formula of magnesium sulfate, and let's determine the molecular mass. So the molecular mass, so we need the mass of magnesium times the number of magnesium atoms plus the mass of sulfur times the number of sulfur atoms plus the mass of oxygen times the number of oxygen atoms. So I'm going to need everyone's help here. We know the mass of magnesium is 24.31 gram per mole. In our formula, how many magnesiums do we see? In our formula, how many
One.
One, exactly. Would someone like to tell me what is the mass of sulfur? What is the molar mass of sulfur in the periodic table? 32.07. So we take our 32.07 gram per mole, and then we multiply it by the number of sulfur atoms. And how many sulfur atoms do we have?
One.
One, exactly right. For the mass of oxygen, we know it's 16.00 gram per mole. And how many oxygens do we have? How many?
Four.
4, exactly. So if we add up these masses using our calculator, you should get a value of 120.38 gram per mole of magnesium sulfate. Does this make sense to everyone? Does this make sense to everyone? When you punched it into your calculator, did you get the same result? Try it on your own with your calculator. Make sure you're able to get the same numbers, because I'd be more than happy to walk through the calculator calculations and how to enter things into your calculator during the later part of this lab. I really want to make sure everyone's comfortable using the tools that they have at their disposal. Now, we're very good at calculating molar mass, and this brings us to our next topic, which is the idea of hydrates. So hydrates are molecules containing a defined number of associated water molecules as part of their chemical formula. It's not a wet solid. The water is part of the chemical formula and it impacts the properties. Hydrates are unique chemical species. So for example, cobalt chloride without any water has a blue color, while cobalt chloride hydrate with these associated water molecules is a pink color. We call the ionic compound with associated water with this dot, we call it a hydrate. If we have no water molecules associated, we call this form the anhydrous form. So, hydrates are unique chemical species. They have different colors, different masses, different properties. Does that make sense to everyone? So it's not just a wet sample, it's a unique chemical compound. Now, what we can do in this experiment is we're looking at the comparison between magnesium sulfate and magnesium sulfate hydrate. And we don't know how many water molecules are associated with magnesium sulfate. However, what we can do is we can compare the molar mass of our anhydrous and our hydrate, and we'll notice something that's really interesting. So let's look at the molar mass of cobalt chloride and I'd like you to compare it to the molar mass of cobalt chloride hydrate. So let's start with this first example. So for cobalt chloride, we'd need the mass of cobalt. What is the mass of cobalt in our periodic table? What mass do we see for cobalt?
58.93.
58.93 gram per mole, perfect. And how many cobalts do we have?
1.
1, yep, exactly. Chlorine has a mass of 35.45 gram per mole. And how many chlorines do we have?
2.
2. So if we add our masses together, so we have 58.93 plus 35.45 times 2, and that gives us 129.83 gram per mole of cobalt chloride. Let me rewrite that. Okay, now let's look at our hydrate. So the molar mass of our cobalt chloride hydrate. So the anhydrous portion is going to be exactly the same. We still have our cobalt. We still have our chlorine. Now looking at these 6 waters, how many hydrogen and oxygen atoms do we have in our 6 water molecules?
12 hydrogen.
Yep, we have 12 hydrogens. 6 times 2 gives us 12, and 6 oxygens because 1 times 6. You can also draw it out. That makes it really easy to see, and then you can just count visually. So really don't be shy to count. If it works, it works. Whatever method works for you. Okay, so we have 12 hydrogens and we have a molar mass of 1.00 gram per mole for hydrogens, and we have 12 hydrogens. Finally, we have a mass of 16.00 gram per mole for oxygen, and we have 6 oxygens. So now if we add our masses together, you can think of it this way. We have a 129.83 gram per mole of cobalt chloride. Oh, sure. I was using another periodic table with a slightly different mass, but yes, you can write it as 1.01. That's no problem at all. So we have 1.01 times 12 plus 16 times 6. And we also have a mass of 108.12 gram per mole. And this is coming from our water molecule. So in turn, we have a total molar mass of our hydrate equal to 237.95 gram per mole of our hydrate. Does everyone notice how if we compare the hydrate and our anhydrous compound, that there's a substantial difference in their molar mass, how their masses are different? Does everyone see how the masses are different for these 2 compounds?
Yes.
So this is really important because if you start with a sample of hydrate and you apply heat, you will in turn lose your water molecules associated with your hydrate. So, for example, if you start with your cobalt chloride hydrate and you heat it, at the end of the heating process, you will only have cobalt chloride. Okay, now, how can we use this? How can we use this? By measuring our initial mass, so by measuring the initial mass and comparing it to our final mass, we can use the idea of conservation of mass. So mass is conserved, and as a result, any mass that is lost is the mass of water lost. Right? Because we're losing water when we heat our sample. Does that idea make sense? Right? We're losing water. The mass that we lose is the mass of water. So then, we can record the mass of our hydrate. We can record the mass of our anhydrous sample. And we can figure out the mass of our water lost by taking the mass of our hydrate minus the mass of our anhydrous sample. So now we have the mass is provided. Okay. Next, what we're going to do is we're going to determine what is known as the formula ratio or empirical formula. And for the empirical formula, we have to use the following step-by-step guide. First, you need to find the mass of each element or compound, the mass. Then you need to calculate the molar mass of each element or compound. So now that we have that, in the step 3, we are going to calculate the moles of each element or compound. And in step 4, we're going to find the simplest ratio of moles of each element. Now, before we apply this procedure to our hydrate example, let's look at something really simple. So first, let's talk about doing our mass to mole conversion. So we can go from mass to moles using our molar mass. So for example, if we have a mass of 12.00 grams of oxygen, we can use our molar mass and use unit analysis to convert this grams of oxygen into moles of oxygen. So how do we do that? Well, the molar mass of oxygen is of the form 16.00 grams of oxygen per mole of oxygen. If I'm going from grams to moles, now this is where what I taught you in unit conversions is going to be really helpful. If we're going from grams to moles, what unit do I put on top? What do I need on top? If I'm going from grams to moles, What units do I
Mole.
put on top? Moles, exactly right. In this case, it would be moles of oxygen. And if I'm going from grams, what units do I put on the bottom?
Gram.
Exactly. So now I fill in my molar mass. So we have 1 mole of oxygen per 16 grams. So just as a shortcut to go from grams to moles, you divide by your molar mass. So if we punch that in, we see grams cancel. We're left with moles. So we have 12 over 16. That gives us 0.75 moles of oxygen. We technically write this as 7500 because we have 4 sig figs. Does this idea make sense? Does this mass to mole conversion idea make sense?
Yes.
Let's look at another example. Let's suppose we are trying to go from 10.00 grams of magnesium and we wanted to calculate the moles of magnesium. What conversion factor would we use? What molar mass do we use for magnesium? What molar mass do we use?
24.31 molar
Yep,
each gram.
exactly right. And just like before, we put moles on top and we put grams on the bottom. And if we punch that in, we have 10 over 24.31. And that in turn gives us 0.41135 moles of magnesium that we round to 0.4114 moles of magnesium if we're reporting our final answer. Does this make sense to everyone? Everyone
Yes.
comfortable with this? You may want to reference these calculations that I've shown you, and I have similar versions on your on the Canvas page. Now let's look at an example where we're dealing with a molecule. So remember how we talked about magnesium sulfate, and we said all the way at the beginning that magnesium sulfate, we calculated its molar mass to be 120.38. Okay, so let's suppose I have 1.00 grams of magnesium sulfate, and I wanted to calculate the moles of magnesium sulfate. And I want to go from grams to moles. Well, fundamentally, has anything changed in our unit conversion process? Can we still cancel our units by putting moles on top and grams on the bottom? Yeah, nothing has changed. So we just like before, to go from gram to moles, we divide by our molar mass. So in this case, we divide by 120.38, and that gives us 0.008307 moles of magnesium sulfate that we round to 0.00831 moles of magnesium sulfate. Does this example make sense? Does this example make sense to everyone?
Yes.
Likewise, suppose that we had 2.00 grams of water. So H2O, we know in 1 mole of water, we have 18.00 grams. And that in turn allows us to calculate the moles of water which would be 0.1111 moles of water, which gives us 0.111 moles of water following sig fig rules. Does that make sense? Does that make sense to everyone?
Yes.
So, okay, so how do we deal with the empirical formula? How do we deal with the empirical formula now that we know how to do mass mole conversion? So step 1, we determine the mass. Step 2, we determine the moles. And step 3, we find the simplest ratio of moles. Okay. So let's look at an example where we have 40.00 grams of calcium and 16.00 grams of oxygen in our sample. So then we have our masses. So step 1, we finished. Step 2, we calculate the mole. So the moles of calcium will be 40.00 grams of calcium. And what is the molar mass of calcium? In 1 mole of calcium, how many grams do we have? 40, yep. We'll use 40.00 just to keep the numbers a little bit cleaner. And that gives us 1.000 moles of calcium. For our moles of oxygen, we have 16.00 grams of oxygen. And in 1 mole of oxygen, we have 16.00 grams, and that gives us 1.000 moles of oxygen. So now for step 3, we're looking at the ratio and the simplest ratio of the moles of each element. So we take the moles of oxygen over the moles of calcium, and that gives us 1.000 moles of oxygen over 1.000 moles of calcium, which we can think of as 1 mole of oxygen per 1 mole of calcium. In other words, our formula would be calcium 1, oxygen 1, or calcium oxide. Does everyone see how the ratio is directly tied to our formula? Does that step make sense to everyone? Does that step make sense to everyone?
So if it's 3 mole to 1 mole, then the formula gonna be 3 to 1.
Yes, yes. And I'll actually talk about that example. So let's suppose we have a sample with 39.00 grams of potassium and 8.00 grams of oxygen. Let's do a follow-up. So we have our masses figured out. Next, we need to calculate moles. So for our moles of potassium, we have 39.00 grams of potassium. In 1 mole of potassium, we have how many grams? What's the molar mass of potassium in this case?
39.
Yep. So then that would give us 1.000 moles of potassium. For our moles of oxygen, we have 8.00 grams of oxygen. In 1 mole of oxygen, we have 16.00 grams, and that gives us 0.500 moles of oxygen. In general, when you're figuring out your empirical formula, you divide by the smallest number of moles. So we're going to divide by the moles of oxygen. So we take 1.000 moles of potassium over 0.500 moles of oxygen, and that gives us 2 moles of potassium per 1 mole of oxygen. So how many potassiums would we have in our formula?
2.
2. So it would be K2O1, which is equivalent to K2O. Does that make sense? Does this idea of calculating the empirical formula make sense for this example?
Yes.
So, for metal oxides, there is a unique procedure used to determine the empirical formula. So in this case, we start with our metal, and then we heat our metal. And this allows our metal to react with oxygen. So our metal reacts with oxygen to make a metal oxide. Now, at the end of this process, we have our metal oxide, MO. So by conservation of mass, any mass gained during heating is the mass of oxygen in our metal oxide. The oxygen that ends up in our product comes from the oxygen in air. As a result, you can think of it this way. So you have your metal, it reacts with oxygen, and we end up, so if we have the mass of metal, we end up with our final mass of our metal oxide. And any mass gained must be equal to the mass of oxygen. So then, the mass of metal is known. We get that from weighing. So we can write down the mass of our metal. Okay. The mass of our oxide is known. We get that via weighing. And then as a result, the mass of oxygen is going to be equal to the mass of our oxide minus the mass of our metal before heating. Does this equation make sense?
Yes.
So then, once we have the mass of each element, we can find the empirical formula. So let me show you an example of this. Give me one moment. I'm just going to punch some numbers into my calculator really quickly. Suppose we take 3.5 grams of lithium and it's reacted with oxygen to yield one moment, 15.00 grams of a lithium oxide. Okay. From this information, let's calculate the empirical formula of lithium oxide. Now, there are two ways of doing this. The first way is if you remember what we discussed in lecture today, if we know the charges, we can figure out the formula immediately. So this is known as the charge method. Does everyone remember this from class?
Yes.
So that's one way. It doesn't work for transition metals, so let's talk about the calculation method that we'll be doing in the lab. So we know the mass of lithium, which is our metal, is 3.500 grams. We know the mass of our lithium oxide is 15.00 grams. So then the mass of oxygen is equal to 15.00 grams minus 3.500 grams, which gives us 11.500 grams of oxygen. Notice we're referring to atomic oxygen because that oxygen is the mass of oxygen as part of our chemical formula. Does this first step make sense?
Yes.
Now, we have the mass of lithium, so we can calculate the moles of lithium. So 3.500 grams. And what is the molar mass of lithium? In 1 mole of lithium, how many grams do we have, roughly?
6.94.
Yep, and yep, perfect. So plugging that in, we get 0.50432 moles of lithium. It's really important that you do not round until the end. But when you're reporting your final answer in your lab notebook, then you round following sig fig rules. So this is what would go in your notebook, but this top number is what you'd use for your calculations. Does that make sense?
Yes.
So you don't round until the end, but you round when you're writing down your final answer in your notebook. For our moles, for our mass of oxygen, we have 11.500 grams. So our moles of oxygen, in 1 mole of oxygen, we have 16.00 grams. So we take 11.5 divided by 16, and that gives us 0.06250 moles of oxygen. Okay, now that we have let me punch this in one more time. Sorry, there's a typo. 0.71875 that we round to 0.7188 moles of oxygen if we're writing down our final answer. Now we look at our mole to mole ratio. Now we look at our mole to mole ratio. So we take the moles of oxygen divided by the moles of lithium. Let me just check one thing really quickly. So taking our mole to mole ratio, we have 0.7188 moles of oxygen over 0.0543 or 0.5043 moles of lithium. And that in turn gives us 1.425 moles of oxygen per 1 mole of lithium. Now, if you get a number like this at the end of your experiment, this is a sign that you likely need to redo your trials. You should get relatively clean whole number ratios for your mole to mole ratio. So you may notice in one of the videos that they have to redo. So let's pretend that they redo this experiment because they notice their mole to mole ratio is not a whole number. So they likely didn't get a complete reaction. And in their redo, they took 3.500 grams of lithium and reacted it with oxygen. And this time, when they performed the experiment accurately, they got a final mass of 7.500 grams of lithium oxide. So when they redid the experiment, we know our grams of lithium is 3.500 grams of lithium. Our grams of lithium oxide is 7.500. And so our grams of oxygen in the second trial would be 7.500 minus 3.500, which gives us 4.000 grams of oxygen. Just like before, from our grams of lithium, we can calculate in turn the moles of lithium. So if we have 3.500 grams of lithium, in 1 mole of lithium, we have 7.000 grams, which gives us 0.5000 moles of lithium. For our grams of oxygen, if we have 4.000 grams of oxygen, we can figure out the moles of oxygen as 4.000 grams of oxygen times 1 mole of oxygen over 16.00 grams. That gives us 0.2500 moles of oxygen. And this data is what you'd get if your experiment was performed with reasonable experimental technique and you're really careful to avoid introduction of undesired masses. So now that we have our moles, we can take our mole to mole ratio. So our moles of lithium over our moles of oxygen. We have 0.500 moles of lithium over 0.2500 moles of oxygen. And that gives us 2 moles of lithium per 1 mole of oxygen. Your numbers, when you take your ratio, you should end up with nice whole numbers. And that gives us a formula of Li2O for lithium oxide. Does this example make sense? Does it make sense to everyone how we calculate the empirical formula from the mass of each of our elements? Okay, so these are the calculations that you'd need to be familiar with for part A, for our metal oxide analysis. And I have another sample calculation available on the Canvas page. Let's look at part B now. Let's look at part B, which is our hydrate analysis. So as we discussed, we are looking at the example of cobalt chloride hexahydrate. So we start with our hydrate, and if we heat our sample, we lose water, and we isolate the anhydrous form. So we can record the mass of our hydrate, and we can record the mass of our anhydrous form. We know that the mass of water is equal to the mass of our hydrate minus the anhydrous form. That's what we established for our hydrate analysis. Now, once we have the mass of our anhydrous form, in this case cobalt chloride, and once we have the mass of our water lost, we can calculate the empirical formula. Of the hydrate. So we've figured out the masses. So let's look at a sample data set. A cobalt chloride hydrate had a mass of, so let's look at let's just refresh a little bit on our known molar masses. So I'm just going to put these on the side here. Okay, so our cobalt chloride hydrate had an initial mass of 0.6141 grams. The sample was heated and a final mass of anhydrous material was found to be 0.3324 grams. So from this information, we can calculate the empirical formula of our hydrate. So we know that the initial mass of our hydrate, was 0.6141 grams. We heated our sample and we have the mass of our anhydrous material, which has the formula cobalt chloride, was found to be 0.3324 grams. Now we need to calculate the mass of water by taking the mass of our hydrate minus the mass of our anhydrous sample. Which gives us 0.2817 grams of water. So now that we know the mass of our anhydrous sample, we can then calculate the moles. So we know the moles of cobalt chloride would be equal to the mass divided by our molar mass. So we know in 1 mole of cobalt chloride, we found it had a molar mass of 129.83 grams. That gives us a moles of 0.002560 moles of cobalt chloride. Likewise, from the mass of water, we can figure out the moles of water. So we have 0.2817 grams of water. In 1 mole of water, we have 18.00 grams. And punching that into our calculator, that gives us 0.01565 moles of water. So once we have the mass of our anhydrous sample in water, we calculate the moles. Now that we have the moles, we take the mole to mole ratio. So we look at how many moles of water do we have per mole of cobalt chloride. So we have 0.01565 moles of water over 0.002560 moles of cobalt chloride. And that in turn gives us a mole to mole ratio of 6. You always place the greater number of moles on top. Yes, of 6.113 moles of water per moles of cobalt chloride. And that can be rounded to the nearest whole number of 6 moles of water per 1 mole of cobalt chloride. Your experimental data won't be perfect, so you may not get exact perfect whole numbers. And only for this experiment, and only in this case, you can round to the nearest whole number. So that would give us how many water molecules in our hydrate. What did we calculate? How many water molecules do we have in our formula? How many water molecules did we calculate? How many moles of water did we calculate? 6. So we put a 6. And this allows us to figure out the formula of our hydrate. Does this example make sense? Does this example make sense to everyone? Any questions on this example? So that's all I have for today's lab lecture.